Mass losses from glaciers and ice sheets are currently the main contributor to sea level rise, and this contribution is expected to increase in the forthcoming decades and centuries. Most of these losses result from melting and sublimation at the glacier surface, from submarine melting at the parts of the glacier in contact with seawater, and from acceleration of ice flow, which results in an increase of iceberg calving. All of these processes are favored by increased temperatures of the atmosphere and the ocean, exacerbated by climate change.
Within the European Commission-funded project INTAROS, our team, formed by researchers from Universidad Politécnica de Madrid and from the Geological Survey of Denmark and Greenland, GEUS, is investigating the mass losses of marine terminating glaciers and ice sheets. In particular, we are interested in estimating the mass losses in solid and liquid forms. Estimating their proportions is essential to understand the processes controlling the mass losses and also to be able to forecast their future evolution under various scenarios of greenhouse gas emissions.
Before proceeding, we need to introduce some basic terminology.
To simplify the presentation, let us assume that the marine terminating part of the glacier is not floating, as shown in the cartoon. The mass losses at the glacier front are referred to as frontal ablation. It includes iceberg calving, submarine melting, and melting and sublimation at the emerged part of the glacier front. The latter is usually negligible and we will not take it into account. As these components are very difficult to evaluate separately, frontal ablation as a whole is often approximated by the ice discharge through virtual flux gates defined near the glacier front. The flux of ice through such flux gates is referred to as solid ice discharge or simply ice discharge. The amount of frontal ablation is nearly equivalent to that of solid discharge, provided that the flux gate is close to the calving front and that there are no front position changes. Otherwise, correction for both factors should be applied. The meltwater produced at the glacier surface reaches the bed through crevasses and moulins and flows subglacially towards the fjord. This freshwater flux entering the fjord is commonly known as subglacial discharge, and it will be a key control on the submarine melting of the glacier front.
Ken Mankoff from GEUS will explain us how freshwater and solid ice discharge for Greenland are being calculated.
Before we can estimate the amount of submarine melting and iceberg calving that happens at a glacier terminus, we need to know the total amount of ice flux across that terminus. The total amount is split into some proportion of iceberg calving and submarine melting, and these are controlled primarily by two other parameters. This is the temperature of the fjord water, especially at the bottom, and the amount of subglacial discharge flowing out at the base of the glacier. Upstream from the terminus, we calculate ice discharge across flux gates. For every marine terminating glacier in Greenland, we place flux gates about 5 kilometers upstream from the terminus. We look at the ice thickness from the bed machine dataset, and we look at the ice velocity from measures and Sentinel ice velocity products. Multiplying these together, the thickness times the velocity times the density, gives the mass of ice in gigatons. Not everything is known. Often ice thickness is unknown, in which case we estimate it by looking at the known thickness and velocity relationship elsewhere. Deep fjord water temperature can only be measured by dropping a thermometer into the fjord to measure it until some remote sensing method is developed. Finally, we also estimate subglacial discharge at every outlet glacier. This is done by, again, using ice thickness and adding in basal topography to drive a flow routing algorithm that predicts where water will flow under the ice. From this, we can then estimate what the upstream hydrologic basin is for each outlet and include the subglacial discharge from regional climate models. We use two regional climate models, or RCMs, the Hirham and Mar RCM. These provide the water inputs. That's both melted ice and also snow and rain on the ice. At Gaius, we have developed a solid ice discharge and a liquid freshwater runoff product to meet these needs. The solid ice discharge product is what we call operational. That means it's a live product that updates about every 2 weeks with a 1-month lag. The ice discharge covers all marine terminating glaciers from 1986 through last month. On the other hand, the freshwater runoff product has been computed once, but covers 1958 through 2019. It has daily temporal resolution and stream level spatial resolution.
The Greenland freshwater runoff here has a source link, and if you click on this, you will be taken to the Gaius Dataverse, and again find the Greenland freshwater runoff product there. This product is not simple to download because it is 200 files and about 12 gigabytes. However, here we provide a small bash shell script that can download the dataset for you. Future versions will be easier to download. From the INTAROS solid ice discharge dataset, the link takes you to the Gaius Dataverse. Here is the Gaius Dataverse ice discharge page. There are various files here. The .NetCDF are for more technical use, and the CSV can be opened with any spreadsheet software. There is discharge provided at the gate level, sector, region, or the GIS is the Greenland Ice Sheet total discharge. We'll view that file here by downloading, opening in spreadsheet software. And the first column is the date of the discharge, and the second column is the gigatons per year. Scrolling down towards the bottom, the most recent estimate shows that Greenland at this point in time is discharging a little bit over 500 gigatons of ice per year.
We've seen how to obtain the freshwater and solid ice discharge. Now we'll see how to use numerical approaches to estimate the partitioning of ice discharge into iceberg calving and submarine melting. In this case, we'll listen to Eva de Andres from the Group of Numerical Simulation in Science and Engineering in Spain.
To build the numerical model, we first need to identify the different components of the system which are subject of simulation. In our case, we should think in two components: the ice one, which is the tidewater glacier, and the ocean one, which would be the fjord where the glacier ends to. For the ocean component, we'll also see the Buoyant Plume simplification, which will allow us to reduce the time of computation. The aim of the glacier fjord or the glacier plume models will be to estimate the ice discharge partitioning into calving and submarine melting. From the fjord component perspective, we use the Navier-Stokes formulation where the equations driving the fluid dynamics are those of conservation of mass, momentum, heat, and salt. Density of seawater is defined as a function of temperature and salinity by means of a nonlinear equation of state. The model includes freshwater input at the freezing temperature through the grounding point, which represents the subglacial discharge. This freshwater input is compensated with a seawater output at the fjord mouth. The 2D configuration of the model would be partially compensated by a proper choice of the viscous and diffusive coefficient values. At the glacier fjord boundary, we include the thermodynamic equilibrium at the glacier fjord interface, considering the freezing temperature as a function of salinity and pressure and the heat and salt budget equations. This model allows us to estimate the melt rate of the submerged ice front. The fjord circulation and submarine melt models require as input data the fjord bathymetry, the subglacial discharge rates, and water temperature and salinity. The outputs of the models are the evolving velocity, temperature, salinity, and pressure fields across the fjord and the melt rates at the glacier front. From the ocean side, instead of simulating the general circulation of the fjord waters, we could just calculate the submarine melting taking place at the glacier front by simulating a simple buoyant plume. This buoyant plume is the result of the subglacial freshwater discharges entering into the salty fjord waters. Here, we see an example of a buoyant plume at the front of Stork Glacier in Greenland. If we assume a fixed width for the discharging channel and consider that the plume properties are constant along the channel width at a given depth, we can call it as the line plume model. The line plume model is steady in time, and the only independent variable for tidewater glaciers is the vertical dimension, so it is strictly a one-dimensional model that considers constant plume properties along the plume thickness. The evolution of the plume properties along the vertical tidewater phase is described by 4 ordinary differential equations describing the flux conservation of mass, momentum, heat, and solid. The plume model is closed using a thermodynamic equation of state to calculate the plume and ambient fjord water densities, and the same submarine melt model as described before for the fjord model. To calculate the submarine melting and the plume properties, we'll need to initialize our model with the subglacial discharge fluxes and set the temperature and salinity of the ambient fjord waters. Once we have all the equations together, we need numerical methods to solve them. For the glacier model, we use the software Elmer Ice, which is based on the finite elements method. For the ocean components, the software MIT GCM, which is built on the finite volume method, is used to solve the fjord circulation model, while a MATLAB routine is used to simulate the buoyant plume model. But how can we obtain information about the glacier fjord system as a whole? We need to couple the different components to obtain a single ice-ocean couple model. Let's see how we made it. We start by running either the fjord or the plume model for a discrete period of time from which we'll obtain an estimate of the submarine front melting for that period. This melting is then converted to a change in the shape of the glacier front, which produces a new glacier geometry. After remeshing, the glacial model runs for the same discrete period of time as the ocean component, obtaining front position changes as a result of both ice flow and calving events. Consequently, the fjord or the plume domain changes and needs to be remeasured for the next step. This mechanical and asynchronous coupling is automatically repeated until the end of the simulation. Now let's use our coupled models to simulate a real glacier fjord system in the Arctic. In this case, we've chosen the Hansbreen-Hansbukta system in southwest Svalbard. Hansbreen is a tidewater glacier of about 16 kilometers in length with a 1.5 kilometers wide calving front, which reaches maximum velocities of almost 200 meters a year during the melt season. Hansbukta is the proglacial fjord where Hansbreen flows into, and it is around 2 kilometers long, with bathymetry varying between 25 and 80 meters depth. As we've seen earlier, to solve our sets of equations, we need to define the glacier and fjord geometry, as well as set the initial and boundary conditions for the different variables. For Hansbreen Glacier, we have observations on surface velocities, surface mass balance, ice melange coverage, and front positions within the melt season of 2010. On the other side, we have observations of fjord temperature and salinity for the overlapping period of April to August of 2010. Here is the scale of our Hansbreen-Hansbukta system in 2 dimensions. Let's see the setup for each component. The glacier domain is divided into a rectangular mesh with 10 vertical levels and a horizontal grid resolution increasing from 50 meters in the upper glacier up to 25 meters close to the front. The time step for the glacier component is 1 week. The fjord domain is divided into a rectangular mesh of 90 vertical levels and 200 horizontal levels. With the aim to obtain more accurate melt rates, We use a high spatial resolution grid of 1 meter for the very first 100 meters next to the front and then linearly increasing to the end of the fjord domain. The time step for the fjord circulation model is set to half of a second to ensure the stability of the solution. For the line plume model, we just set the tolerance for the solution and the depth of the grounding point, which will automatically vary as the ice front moves forward or backward. To evaluate the goodness of our coupled models, we show here the model performance against the observed front positions. To get these results, previous sensitivity analyses have been done to different parameters. What we see in this figure is that both the glacier plume and the glacier fjord coupled models are able to reproduce their observed front positions under some specific configuration, which is represented by the green lines in this figure. We also observe that every one of these downward steps correspond to a calving event calculated by the models. Therefore, we could estimate how much ice is lost due to calving at the end of the simulation. However, we should consider that previously to calve, part of the ice front has undergone submarine melting, so we should include this in our estimations. Here, we see the submarine melting taking place at different depths of the ice front for every week of the simulation. Both models show that submarine melting increases as the summer progresses, which is consistent with the warmer fjord temperatures and the higher subglacial discharges. Although the submarine melt profiles appear to be different in each model, they both show similar rates of submarine melting, reaching up to 20 meters a week at the end of the simulation. If we contrast the evolution of the linear cumulative calving and submarine melting along the simulation, we see that both mechanisms of frontal ablation follow a very similar trend and magnitude. Given that we have the submarine melt profiles and that calving always results in a vertical ice front, we can calculate the frontal ablation area lost by each mechanism and obtain the ice discharge partitioning of Hansberry during the melt season of 2010. We obtained that submarine melting represents between 60 and 70% of the discharged ice, while calving accounts for 30 to 40% of that ablated area. If we aim to estimate the ice discharge partitioning in volume, we would need to use 3D models. But we can also make some simplifications in our Hansberry-Hansbukta system and get a rough estimation. If we consider that calving rate is the same along the Hansberry front and assume that there is no subglacial freshwater discharge outside the plume channel, we get these other numbers, which largely differ from those obtained from our 2D coupled models.
We are coming to the end. We have seen how INTAROS data catalog can be used to download data on solid ice discharge and meltwater runoff, and how can models be used to separate frontal ablation or ice discharge into its two main components, iceberg calving and submarine melting. More detailed information can be found in a list of related publications included in the deliverable 670 document available at the following website. Of course, much work remains to be done. This is how science works. Scientific knowledge is accomplished as the result of a continuous set of small contributions by an ample community of researchers. We hope to have contributed within INTAROS to fill some gaps in the knowledge of the Arctic climate system and its interaction with the geosphere and the biosphere,